Hey everybody. Today we're talking about rational functions and their graphs. A rational function is just a ratio of polynomials, a function that can be written in the form p over q, where p and q are both polynomials. A very simple example is the reciprocal function 1 over x. Here, p is 1 and q is x. Here's a couple more complicated ones. X squared plus 1 over x cubed plus 8x minus 2, and x to the fifth over 4x squared minus 8x plus 4. In each case, we've got one polynomial divided by another. One last example, 3 plus x squared. This is a polynomial, but it's also a rational function. We can take the denominator, q of x, to just be 1. The domain of any rational function is going to be all real numbers except for those that make the denominator 0. So if we need to find the domain of a rational function like this one, we set the denominator equal to 0 and then solve. Those solutions are going to be the values that are omitted from the domain of f. In this case, we have a common factor of 2x, so we pull that out. And then we factor x squared plus 3x minus 4 as x minus 1 times x plus 4. Setting each of those factors equal to 0, we get solutions x equals 0, 1, and negative 4. Again, those are the values that are left out of the domain of f of x. In interval notation, our solution is negative infinity comma negative 4, union negative 4 comma 0, union 0 comma 1, union 1 comma infinity. All of those endpoints being omitted. One distinctive feature of rational functions is that they frequently have asymptotes, straight lines that the graphs approach over time. The function y equals 1 over x, I think, is a really good example to illustrate this idea. Here we have a horizontal asymptote of y equals 0. When x gets really, really large in either direction, the graph gets closer and closer to that horizontal line. We also have a vertical asymptote of x equals 0. When x gets very, very small, the graph gets closer and closer to that vertical line. This is a very useful fact. The function 1 over x to the n has a horizontal asymptote of y equals 0 for any positive n. Now, since we're considering rational functions in this video, n should be an integer, but in fact, this fact holds as long as n is just positive. All it's saying is that when x gets very, very large, the denominator is getting very, very small. And so the function gets closer and closer to the line y equals 0. The function y equals 1 over x squared, I think, illustrates this point pretty well. As x gets bigger in either direction, the value of the function gets smaller, the graph gets closer to y equals 0. More generally, we can always determine horizontal asymptotes by looking at the highest power terms in the numerator and denominator for any rational function. Here's a very algebraic description. I've written generic polynomials in the numerator and denominator, so this is any rational function. Then, to determine the horizontal asymptotes, I just look at the highest power term. A sub n x to the n, the highest power in the numerator, and b sub m x to the m, the highest power term in the denominator. Rewriting it, I can say a sub n over b sub m x to the n minus m. So we want to consider that exponent, n minus m. If n is bigger than m, that's going to be positive. That exponent is going to be positive. So when x gets really, really large in either direction, this thing is going to grow without bound. We're not going to have a horizontal asymptote. So that's going to be the case when the polynomial in the numerator of the rational function has higher degree than the polynomial in the denominator. Conversely, if the denominator has the higher degree, m is greater than n, then the exponent of that x to the n minus m is going to be negative. And as x gets bigger and bigger, that's going to go towards 0. It's going to get smaller and smaller. We're going to have a horizontal asymptote of y equals 0. Finally, if the degrees are equal, n equals m, then x to the n minus m is going to be x to the 0, or 1. We're going to have a horizontal asymptote of y equals a sub n over b sub m. Let's do a few examples. Find all horizontal asymptotes, if any, of these rational functions. This first one has a higher degree in the denominator. So according to that previous slide, we're going to have a horizontal asymptote of y equals 0. To explain a bit more, this function's end behavior is going to be the same as x to the third over x to the fifth, which is the same as 1 over x squared. And as x gets bigger and bigger in either direction, that's going to get closer and closer to y equals 0. The second function has a higher degree in the numerator. So when x gets bigger and bigger and bigger, this function's going to behave like x squared over x. It's going to grow without bound, and we're not going to have a horizontal asymptote. Finally, this function has the same degree in the numerator and denominator, so we have a horizontal asymptote of y equals 7/3, the ratio of those leading coefficients. We can determine roots and vertical asymptotes of rational functions by finding the zeros of the numerator and denominator respectively. If the numerator is 0 but the denominator isn't, you've got a root of that rational function. If the denominator is 0 but the numerator isn't, you have a vertical asymptote for that rational function. And if they're both 0, you probably have to do some more work. The graph will either have a vertical asymptote or a hole, and you have to do a little bit of work just to figure out which. Notice in that case, you definitely do not have a 0 of the function because the value x equals c will not be in the domain. It makes the denominator 0. Seriously, do not assume that just because the denominator is 0 for a rational function that you have a vertical asymptote. You could just have a hole. I think a good illustration of that problem is the function x squared minus 1 over x minus 1, which when you graph it looks just like y equals x plus 1, but with a hole at x equals 1. Algebraically, here's how we could determine that we have a hole and not an asymptote. As I said a couple slides ago, when both the numerator and denominator are 0, there's going to be a common factor in the numerator and denominator. We want to find it and cancel it. Here, the numerator factors as x minus 1 times x plus 1. And so, as long as x is not equal to 1, this simplifies to y equals x plus 1. Now, this does not have a 0 in a denominator when x is equal to 1, so we're not going to have a vertical asymptote. Instead, we just have a hole in the graph at x equals 1. Overall, the function just looks like y equals x plus 1 as long as x isn't 1. Let's look at an example where the opposite happens. This function, g of x equals x minus 1 over x cubed minus 3x squared plus 3x minus 1, has a numerator and denominator equal to 0 when x equals 1, just as in the previous example. However, in this case, we do have a vertical asymptote at x equals 1. So we're going to want to find the common factor and cancel it. In this case, if I factor out an x minus 1 from the denominator and cancel it with the x minus 1 in the numerator, I'm going to get 1 over x squared minus 2x plus 1, as long as x isn't 1. In this case, unlike the last one, the denominator is still 0 when x is 1, although the numerator isn't. And that indicates that we're going to have a vertical asymptote in that graph. Let's conclude with one full example. Find all asymptotes and zeros of this rational function. Let's start with horizontal asymptotes. We look at the the highest power terms in the numerator and denominator, 3x squared over x squared. In this case, the degree of the top and bottom are both the same. We're going to have a horizontal asymptote of y equals 3. To say this in words, since the degree of the numerator and denominator are equal, the horizontal asymptote is just the ratio of the leading coefficients. Now let's look for zeros and vertical asymptotes. In order to do that, we're going to factor both the numerator and the denominator. In the numerator, we get 3 times x plus 2 squared. In the denominator, x plus 2 times x minus 5. The denominator is 0 when x is negative 2 and 5, and the numerator is 0 when x is negative 2. So we have a vertical asymptote when the denominator is 0 but the numerator is not. That's at x equals 5. We'd have zeros if the numerator were 0 but the denominator were not. but that never happens. So there are no x-intercepts, no zeros for this function. Finally, we do have a value that makes both the numerator and denominator 0. X equals -2. So we need to look at the simplified version of f of x to determine what happens there. In this case, when we cancel the x plus 2, we get 3 times x plus 2 over x minus 5. When x is -2, the denominator is no longer 0. So the original function can't have a vertical asymptote. It has to have a hole at x equals -2. Here's the graph of the function y equals 3x squared plus 12x plus 12 over x squared minus 3x minus 10. We can see the vertical asymptote of x equals 5, the horizontal asymptote of y equals 3, and the hole in the graph at x equals -2. Notice again, we do not have a vertical asymptote at x equals -2.